Welcome to HotChips 2025. Session 2, Security.
We've selected two excellent talks in security to act as appetizers before lunch here. The first is, you'll see, is a working silicon, really a big step forward in implementing fully homomorphic encryption. That is by the work of Dr. Hongyang from Tsinghua University, and he is an associate professor there. He got his PhD at Princeton, doing a lot of work in in-memory computing, and was recognized with an Edison Prize there, and then came to the Valley and as a postdoc at NVIDIA, and is now, as I said, associate professor at Tsinghua. So, Hongyang.
Okay, thank you, Dr. Papadopoulos, for your kind introduction. It is my great pleasure to be here to introduce our work on a fully homomorphic encryption, or say, FHE accelerator, supporting both CKKS and TFHE schemes in the form of a RISC-V extension coprocessor. So this work is a collaboration between Tsinghua University, Beihang University, and also the InSight1 Technology Corporation. Here's the outline of my talk. I will start by introducing the basics of the fully homomorphic encryption, explaining the necessity and the challenges of supporting multiple FHE schemes. And then I will show an approach of unifying the FHE schemes using a mathematical problem called module learning with error, which enables the RISC-V vector style extension ISA. And next, I will describe the architectural and the microarchitectural design of this programmable and scalable FHE accelerator. And finally, I'll introduce the prototype and the measurements, showing the demonstration for both TFHE and CKKS schemes. Okay, so let me start from what is homomorphic encryption and why it is so critical for the next generation privacy-preserving computing. Outsourcing computation and storage to the cloud has been the enabler for nowadays IT services. However, this service mode of remote storage and computation has the concern of privacy, since the attackers might steal the private data from the lifetime outside the trusted domain. The traditional privacy-preserving technologies require exchange of private keys with the complex higher-level protocols which lack of formal verification of the security. And homomorphic encryption is an emerging technology and concept, providing provable security by eliminating the decryptions in untrusted domain. Here, the plaintext is firstly translated and encrypted into the ciphertext in the data owner's domain, for example, the cell phone on the edge. And then the ciphertext is sent to other parties for computation, which performs an homomorphic encryption translated version of the original task, for example, the neural network inference. Please remember that this computation is done directly on the ciphertext without any decryption. So this limiting any leaking of the semantic information. And then the result is sent back to the edge or the user end and doing the decryption. Then the output of the decryption will be exactly the same with doing the computation directly on the plaintext. So this homomorphic feature gives the name of homomorphic encryption, and the capability of performing any arbitrary functions in homomorphic encryption is the fully homomorphic encryption. The feature of high-level security without restrictions on any complex protocol makes the FHE an ideal candidate for a broad range of privacy-preserving computing applications. For example, this can range from retrieving a photo from the cloud, or performing an AI-based navigation, and even the everyday biomedical diagnosis, and also the recent news on the moving the financial market on-chain. However, as the nature of the cryptography, homomorphic encryption, especially the fully homomorphic encryption, comes with a huge cost of the computation and storage. So how big the problem is? Here we are giving some numbers in terms of dollar per operation for two typical tasks that are widely used in the research of homomorphic encryption. Our cost model is really rough, but consider two portions. So one is the electricity burned in the chip for doing the computation, while the other one is the an estimation on the static cost of purchasing and maintaining the chip and the facilities. And it's amortized across a 5-year lifetime. As you can see here, both neural network inference and logistic regression, the CPU shows 10 to the 4th to 10 to the 5th times a computation cost compared with computing directly on the plaintext. Although the GPU and the FPGA can also significantly accelerate the evaluation of the homomorphic encryption, their higher chip and the facility cost makes the total cost of ownership still very high for the HE services. So therefore, we really need an aggressive ASIC accelerator to enable feasible and affordable fully homomorphic encryption. So why FHE has so much computation overhead? Here we are showing an example inflation of ciphertext for the storage and computation for the basic HE task, which corresponds to a 32-bit multiplication for the floating point number in plaintext. Most of the day's FHE are based on a hard mathematical problem of finding the closest the lattice vectors in a hyperdimensional space. And after performing an FHE encryption, for example, for this typical RLEE configuration, this one 32-bit plaintext will be expanded to 2 high-dimensional polynomial vectors with 111 bits for each element. And this bit width and dimensionality are 2 critical parameters to ensure security. At the same time, the plaintext multiplication is translated into the highly parallel, element-wise, high bit width modular multiplication and additions, introducing a 10 to the 5th times computation overhead. And actually, you can find this kind of inflation anywhere in the homomorphic encryption. Here we provide a more complex and widely considered task, which is the fully homomorphic encryption version of a ResNet-56 inference, showing orders of magnitude inflation in both inference latency and also the peak memory footprint for a CPU system. Moreover, you find that the different plaintext operations actually prefer different homomorphic encryption schemes. For example, the CKKS scheme specialized for approximate SIMD operation in plaintext is an ideal candidate for the matrix vector multiplication for the convolution neural network layers. Well, the nonlinear activation functions, they prefer TFHE-based homomorphic encryption, which can compose any arbitrary Boolean functions. This necessitates the supporting of efficient acceleration with programmability to various FHE schemes. So now let me explain why supporting multiple FHE schemes is so difficult and how we can tackle this problem, this efficiency versus programmability problem, using a RISC-V extension instruction set architecture. In this page, we give a more comprehensive review of the renowned FHE schemes. The development of the FHE scheme can be characterized into 2 directions. So one is doing this Boolean operations for generalization, while the other one is doing the parallel processing for the speed. And the 3 widely discussed FHE schemes, for example, the BGV, BFV, the CKKS, and TFHE, handles very different plaintext representations. Therefore, they are usually associated with very different applications ranging from ID lookup to transciphering. Let's dive deeper into the ciphertext computation here. Cryptography designers carefully choose basic number representation for the ciphertext for each FHE schemes. The CKKS and BGV actually employ ring learning with error problem for encryption, while the TFHE-based scheme employs learning with error and RSGW problem. which leads to very different ranks and shapes of the ciphertext tensors. And besides, the ciphertext formats, although they share a portion of algorithmic vector operations, they still preserve a good amount of unique ones. And you can see that there are several pioneer architectures for dedicated FHE scheme. They only support a subset of the vector operations, causing a limited programmability. One of the fundamental difficulties for doing this a broad range of vector operation is that the inherent typical vector dimensions diverge a lot across the FHE schemes. As shown in the figure on the right, the vector dimension for the TFHE scheme usually fall between 2 to the 9s to 2 to the 11s, while this number for the CKKS usually go way beyond 2 to the 12s. So this gap of parallelization leads to a severe granularity versus scalability dilemma when processing the complex data movement for various vector sizes. And the left figure shown here is an optimistic estimation on some proposed architectures and the key operators for CKKS and TFHE scheme, which illustrates the lack of programmability. To address this curse of wide dimensionality range, we exploit module lattice-based ciphertext representation. The module learning with error, or say MLWE, can be recognized as a general form of the previously mentioned LWE, RLWE, and RGSW problem. And we won't go into details about mathematics here, but we want to state that the key benefit of using this MLWE or module lattice format is that we can confine the inherent vector dimension for these FHE schemes into a narrow range, say from 2 to the 9s to 2 to the 14s. And this enables accelerating a complete set of polynomial vectors operation for various schemes with efficient unified architecture. To put forward a programmable architecture for the FHE, we need to first decompose the operators of HE and then extract the common structures inside it. For example, here we are showing a decomposition of the key operations for the lattice-based FHE, that is the number theory transform, which is called NTT. It firstly loads the input vectors and the associated Tweedle factors into the course, and then performs a highly parallel element-wise modular multiplication. The vector permutations with varying indexings will cascade the computation iterations. So you can see here the three basic types of operation in entity is vector accessing, element-wise computation, and then the vector permutation. And all of them are in very high dimensionality. Here we are showing another example operator, which is a Galois indexing. And it is the key to enable fully RLWE-based homomorphic encryption. As you can see here, the basic characterization of the three operations stay unchanged. And this gives us the opportunity to unify the architecture design for the FHE algorithms. Okay, so here we show a more detailed vector operation set included in our proposed RISC-V extension. The data accessing operation includes both vector and scalar accessing, and the execution operators consider both element-wise operation, for example, this Boolean and arithmetic operations, and also the permutation included operation, which is featured with the data reordering. And this abstraction of fundamental HE operators can cover both CKKS and TFHE schemes. So all of the above effort in the HE operation abstraction comes into a customized RISC-V extension ISA. And here we are using three reserved OP codes in the RISC-V base OP code map, where the custom 0 type is dedicated for the computation, while the other two are used for the vector loading and storing. And this is a more intuitive composition of the FHE version of the vector dot product with the proposed RISC-V extension. It shows the element-wise operation, for example, the VHE mode in the middle, and also the permutation-based operations, such as the NTT and INTT, and then together with the polynomial vector accessing instructions. So here's the example solutions on the integration of the RISC-V extension coprocessor, where the instructions are dispatched from the execute stage of the host CPU. The coprocessor uses its own high bandwidth memory interface to fetch the vector operators. And then the execution instruction can be issued out of order for better utilization. I'll use the next 5 minutes to explain the microarchitectural and architectural design for the specialized RISC-V extension ISA. The compatibility to RISC-V environment allows extending this design at scale by reusing the hardware solutions, for example, the network on chip, and also the software stack, for example, the C++ compiler built by the whole community. In this work, we'll mainly focus on the coprocessor itself, which is named Presto. Presto integrates a graph controller for high-level instruction dispatching and reordering, and also an instruction decoding logic for finer granularity control, and also a processing element array for multi-scheme fully homomorphic encryption computation. The graph controller is implemented as a lightweight RISC-V CPU core to reserve flexibility for future updates with negligible overhead. The extension instruction decoder employs several multi-cycle FSMs to generate the control signal to the PEs. The decoding logic fetches the instructions, FHE instructions, from a 32 depth queue in an out-of-order style governed by the graph controller. The multi-scheme FHE PE array hosts in total 32 pairs of 512-dimensional polynomial vectors. The PE supports a complete set of vector operations for both CKKS and TFHE operators. And moreover, the interconnect allows us to chain the vector operations to exploit temporal and spatial ciphertext locality. And this ciphertext reuse feature is called in-situ processing. Now, let me zoom into the microarchitecture of the Presto coprocessor. We'll go through the control path, PE implementation, and interconnect one by one. To generate the cycle-level control signal to the PEs, Presto includes several separated finite state machines, supporting vector operations from data movement, element-wise operation, and the number theory transform, and so on. The control path is designed to preserve flexibility for future extension. We build a flexible control path from the instruction decoding logic, the FSMs, to the PEs, and to enhance the efficiency of processing large-scale polynomial vectors, which usually combines multiple PEs together in a SIMD style. The control fetch crossbar can be configured in a one-to-multiple broadcast, while the out-of-order execution for the higher data path utilization can also be supported by the asynchronous control fetch from multiple FSMs. The unified PE processing element consists of local storage, computing logic, and data swapping paths. Each PE can be viewed as one entry of the specialized RISC-V extension vector register file. And it is also formed in a 16-bank configuration, which each of the bank holds a pair of 32-element polynomial vectors and acts as a SIMD data path. The intra-PE interconnect provides ample connectivity for the local data swapping. The in-situ processing bank is the minimal computing unit of the Presto coprocessor. The synthesizable latch-based polynomial buffer stores a pair of 32-element, 32-bit vector with a small local register file to balance the programmability and efficiency. The distributed programmable logic performs fundamental element-wise operation, for example, the XOR and shifting and so on, whose combination forms the HE operators. So here is the interconnect for data swapping across the in-situ banks within the PE. The cyclic shifting network on chip steers data for the 16 banks in parallel with a 32-bit channel bit width and a 512-bit per cycle total bandwidth. The cyclic connectivity supports efficient data, matrix transpose which is the compose the butterfly unit of the entity. And it also supports vector rotation, which is the key of the mobile chi operation in the TFHE scheme. When the polynomial dimension goes greater than 512, we need the inter-PE network on chip in the Presto coprocessor to perform a fully configurable data exchange between the PEs. The bandwidth of the interconnect for the inter-PE NOC is also 512 bit per cycle, but shared across 32 PEs. And it turns out that this hierarchical design of NOC guarantees efficient vector permutation with negligible area overhead. And furthermore, we also have a specialized index generator for the Galois operation there. So next, I will show our prototype and measurements. This is the prototype in 28 nanometer CMOS. The area of the PE array in the Presto coprocessor is 5.32 millimeter square, with a local ciphertext storage of 1.125 megabits. The graph controller and the instruction decoding logic takes less than 20% of the area cost here. The chip achieves a maximum throughput of 3.23 million entities per second and also a maximum energy efficiency of 17.1 million entity per joule. The granularity of the polynomial vector is programmable from 512 to 16,384, covering a proper range for the module lattice-based fully homomorphic encryption schemes. And this is for a native element bit width of 32-bit, while the expansion to higher bit widths can be supported within the PE core by trading off the polynomial dimensions. I want to state that this implementation is a fully synthesizable one, which enable easier integration with both ASIC and FPGA. And our recent work has shown the possibility of fully customizing the control logic, the computation logic, and the storage for a better quality of result. We compared our Presto coprocessor with some server-level CPU, and this reference platform is a C++ library customized from open-source HE projects, running on a single thread of the Intel Xeon CPU with 512 gigabytes memory. The left part of the figure shows more than 2 orders of magnitude energy reduction for the typical vector operation in CKKS scheme. And it composes of more than 500x energy saving compared with CPU implementation for a typical bootstrapping task. The Presto coprocessor is also showing a significant latency reduction here. Running at a 1 gigahertz frequency with 1.2 volt supply, the prototype achieves near 100 times speed up compared with the CPU for the CKKS tasks. Besides the evaluation process of the FHE, we also care about the encryption and decryption, which is critical for the user end. Here we are using the BFV encryption and decryption framework to show the programmability. And it shows that the Presto coprocessor achieves more than 50x speed up. We have been discussing the acceleration of HC computation. However, we're letting the communication of the inflated ciphertext as the bottleneck, especially when it goes through the cellular network. And at the same time, we know that the symmetric key cryptography, for example, AES, they have less ciphertext expansion, but suffers potential secret key leaking. Now the question is it possible for the user to spend only a symmetric key encryption level cost, but having a homomorphic encryption level security? And here comes the concept of transciphering. What we're showing here is an example for transciphering from a lightweight AES encryption to the TFHE encryption, where the user end device generates a secret key of the AES, but it is in the form of the homomorphic encryption. And then it sends the encrypted key to the HE cloud at the beginning of the service. The network data processor at the cloud can perform an AES decryption, but is translated into the homomorphic encryption evaluation. And then the output of the network processor will be the plain text of the AES, but is encrypted in the TFHE homomorphic encryption. And the original plain text has never been exposed. Presto coprocessor could be a candidate to embed into the network data processor for the TFHE-based AES transcephering. The figure on the right shows the breakdown in the TFHE version of AES decryption, and you can find that we have more than 70x speed up for the transcephering task. We have also built our software stack to develop and deploy algorithms and characterize the prototype. The developers can code the superclass of the FHE tasks in the open source libraries. And ideally, the IR graph generated by the chorus-grained compiler can be integrated with the RISC-V compiler, and it is an undergoing direction. Right now, we have the APIs to do the executable with the RISC-V extension instructions for the host CPU. And the host CPU is implemented on the FPGA for flexible development and optimization. To help our academic and the industrial collaborators develop HE applications without too much investment in the hardware, we have built our prototype into a small profile dev kit here. And it's a picture of the acceleration board with 2280 M2 format, which includes a small Xilinx Sync FPGA to implement the host RISC-V CPU. And also we can run Linux on top of the ARM cores for software developing and debugging. And this also serves as the PCIe bridge to the starter systems. And this compact profile allows our collaborators to try this out in their own machine, primarily for edge devices. And our next step is trying out our technology in the workstation setup with more Presto core integrated. So here we come to the conclusion. Fully homomorphic encryption provides high level of security, which is an enabler for next generation privacy-preserving computing, for example, financial market on-chain. Various FHE schemes are needed to handle a real scenario application. However, the divergence on the dimensionality for vectors pose challenges for programmable acceleration. We use a module learning with error or MLWE representation to unify dimensionality for SICK-KS and TFHE schemes with a proposed RISC-V extension ISA for multi-scheme FHE. We also built a silicon prototype for the extension coprocessor called Presto, achieve significant speed up compared with the CPU. And here's all of my talk. Thank you for attention. Any questions, welcome. Thank you.
We'll take some questions. Oh, we have one online, please.
Yeah, we have a couple of questions on the applications and overheads of FHE. So the first question is from Cliff Young. Given the large compute and storage overheads you highlighted for FHE, do you see these costs coming down significantly in the near future, or are there specific applications where FHE is already practical despite these challenges? And a related question from Mukul Joshi, can you describe a couple of real-life applications that your implementation can solve today?
Thank you. Those are very good questions. So first question is about the cost, right? I mean, there are several technology directions right now trying to make the cost going down for FHE. For example, some people are using the FPGA to accelerate it. Some people are using the GPUs. Those are very good milestones for FHE, but we can see that there is still a huge gap between the plain text and the ciphertext evaluation right now. So why we're doing the ASICs is because there's a huge cost for designing ASIC, but the chip cost for getting enough computation capability is still cheaper than the FPGA and GPU. So that's why we believe in the future we still need ASICs to make the cost going down. And there's still some way to go, but for some other application like the partial homomorphic encryption, there are already some technology that can do the affordable ones. But fully homomorphic encryption is very important because it's kind of a swap-in technology for a lot of frameworks like the blockchain things, right? So that's also answered the second question you asked, which is where is the application? So one of the key things that we believe is the financial market on-chain, or for example, decentralized finance or something like that, smart contracts, something like that. Some of the information are very sensitive. For example, like when you do the trading, you can want to hold this kind of information for several seconds, and those kind of things need to go into, for example, fully homomorphic encryption, and that's one of the applications we believe. Second thing is the PIR, the private information retrieval. Like you can store your photos from your cell phone to some database, but you don't want to expose to anyone, even if it's attacked, right? So that's where this kind of like homomorphic encryption comes from. Yeah. Thank you.
Hi. Seems like you have answered. My question is,
Could you state your name and affiliation, please?
okay, my name is Jay and work for PsiQuantum. And my question is that you will talk about the application, and do you have any customer pay money for this product or for this technology, or what's the application in that domain? I can see this technology is very potential. It has a lot of huge potential, but the problem is that I want to know what's the how is the penetration, market penetration, and how is the recognition of the customers? Yeah.
Thank you for your question. I mean, first of all, since this work is collaboration between university and company, I cannot disclose too much of the information for the potential customers. But you know, this is really promising direction, because if you just look at some website from Europe, like there's a open source company called Zama, and they're giving a very good amount of instructions and you know, tutorial, and also the marketing analysis on the potential of homomorphic encryption. I think that will be a great reference, and also a follower for their website. I'm a fan of them, their website, so you can find more information there, I guess. But I'm still saying that, you know, for the just recent news, like since the United States is really advocating for the financial market on chain, I think that's the next possibility for this kind of technology, similar technologies.
How is this related to the zero knowledge one?
Yeah, I think we're going to have to cut it off here, and please find Hongyang at lunch, and thank you very much.
Thank you so much.
I'd like to introduce our second speaker in the session. Pay particular attention here. I found in my systems career that customers forgive a whole bunch of things, but not violations of trust of their system. Bryan Kelly is hardware security architect for Microsoft Azure, and he drives the platform that underpins the Microsoft Cloud infrastructure. You may know Bryan from his work in OCP around firmware and root of trust security. Bryan, please.
Yeah, thanks a lot, Greg. All right, so I am the last talk between you and your lunch, so I'll try to make it quick. With that, we'll jump right into deep end, I guess. So according to the World Economic Forum, if cybercrime was a world economy, it will be the third largest after the US and China. It was estimated to have cost the world $9.2 trillion in 2024, and is on target to cost the world $10.2 trillion in 2025. And it's projected to continue to reach $16 trillion by 2030. If cybercrime was a total addressable market today, it would be 5 times the size of the AI TAM. And I say that not to tell you that you're stepping over dollars to pick up quarters, but I want you to get a sense of the challenge that we face in our industry. And we only get to solve this if we work together, because the adversaries that are out there, the syndicates that work to perform this, they work together and are very sophisticated. So at Microsoft, we think about Azure as building the world's computer. And the scale we operate, we manage over 400 data centers across 70 different regions. For instance, in our Dublin data center, we have several data centers in that region. Those data centers collectively comprise of about 2 million square feet of floor space for customer workloads. To put that into some perspective, that size is about the size of 35 American football fields. It's roughly equivalent to 2 million square feet. And the permission to operate at this scale has to be grounded in security. And it is grounded in security. Cyber defense is fundamental to everything we do. It's deeply integrated into every layer of how we design and operate this world's computer. So Microsoft serves billions of customers, allowing us to aggregate security data across a broad spectrum of organizations and consumers. Our presence in this digital world gives us the ability to observe key trends. And right now, Microsoft tracks about 1,500 unique threat groups. And out of those, there are more than 600 nation-state threat actors. And that number generally surprises people. When they think of nation-states, they think of whole countries and just one or two groups of maybe hostile countries. But no, there's over 600. They're very sophisticated in what they do. And of course, tracking all of this for Microsoft relies on AI. It's only possible through AI to track these signals and to remediate and respond. But our adversaries, they also are well equipped with AI and growing in sophistication. And defending against these modern threats is a shared responsibility across teams, organizations, and ecosystems. And our ecosystem at the bottom of the stack, being one of the most foundational components, is absolutely critical. So Microsoft launched a Secure Futures initiative that describes 3 core principles applied vertically through the stack. So these 3 principles are secure by design, making sure when we're designing, we design security in. The other is secure by default, making sure it's on by default. I was speaking with a prominent silicon manufacturer, semiconductor manufacturer, about security, and they actually have rich security in their product. And they said less than 10% of companies that buy their product enable the security. And as we unpacked that and looked at it, it was actually due to barriers in enablement. You know, those companies would buy that product, and of course they'd add their layers of goodness on it to ship the final product. And you know, there's schedules at the end. They always leave security to the end, and then have got to go and redo it and requalify it with security on. So it's important that we lead with security on by default, and it's not an afterthought in the last mile that gets cut for time to market. And then the other one is secure operations. Security should facilitate operations and not be a barrier to it. It should be ingrained in a way that it's natural. When we launched the Secure Futures initiative, Satya Nadella, our CEO, prioritized security above all else and said security is a team sport. And has to go out into not just within Microsoft, but go out into the industry and enable security. And I want to talk about how we do security today in Microsoft and our hardware infrastructure, but then also what we're doing in the ecosystem. And of course, with the Secure Futures initiative, it's a continuous. It's not one and done. We've got to continuously learn, pave paths, and forge new standards where they do not exist. So let's take a look at Azure's hardware security architecture. A hardware security architecture is not a single layer defense, but rather a series of technologies applied at every layer in the system. The layers of the Azure hardware architecture are built on 5 distinct technologies. The CPU and GPU is confidential computing, which provides hardware isolation for workloads. There's a silicon root of trust, which anchors the chain of trust in hardware. There's Azure Boost, which is Azure SmartNIC technology that isolates control plane services from the workload environment. There's hardware management, which is secured on DCSCM with a security chip. And finally, there's Azure Integrated Hardware Security Module, which is a server local security chip for key protection. And I won't have time today to talk about all of these technologies, but we'll focus on maybe just a few and see how far we get through them. And there's a reason for selecting these. These are specifically called out in our annual SFI report. These technologies protect our own security internally and are used for our high assurance workloads. So let's start with hardware security modules, or HSMs. What are they? Well, they're usually large cards or systems that look like this. HSMs were first created in the 70s, primarily for military applications. Their purpose was to secure cryptographic key material and codes. It still happens to be the same use today, although the technology has evolved. They're still considered the gold standard for key management. And they provide protection of the actual keys by isolating them in hardware, the secure execution of the cryptographic algorithms, and are both logically and physically tamper-resistant. So they have some challenges today. And when we look at them, the typical architectures for HSMs, they're separate groups, they're specialized hardware, but deployed separately in separate clusters. And this can create some challenges with scaling them as the compute and AI infrastructure is deployed. The HSMs might have a different lead time in those clusters. So then you, if not forecasted correctly, can run into some delays in deploying that infrastructure. So agility isn't there. And another challenge is they're remotely accessed. When a workload wants to access its keys that are stored in a HSM, it has to do a TLS connection to the HSM, ask it to perform the operation on the key, with the key, and then return the data. And that creates latency, that remote call. So it becomes impractical for some workloads. So we looked at this, and we thought the standard and the gold standard for key management is HSMs, but workloads can't actually make use of it because of this barrier. It's high latency. So to overcome this limitation, and the limitation of central HSMs, we have to reimagine hardware security modules and what it meant. We wanted to still uphold that strong key protection and isolation, but we wanted to eliminate the barriers for adoption. And to do that, it required us to develop a distributed system where we would still have those central HSMs, but now we would have a satellite or a sister HSM that's small enough to scale and be deployed in every system in our fleet. And this brought us to the design of Azure Integrated HSM. And Azure Integrated HSM is a dedicated hardware security module. It strengthens key protection and enables the use of encryption and signing keys while in the HSM bounds without incurring that network access latency. And it does that by being a per server HSM. So this chip scales, it fits in every system in the Azure fleet. It's an in-house ASIC because these kind of chips don't exist on the market. So to scale it and how we scale this chip, I want to talk about some of the lessons learned, what it means to have a per server chip and deploy it in millions of systems globally. So there's lessons that we have to learn from it. When we had these central clusters, that performance could be sized as a central cluster. But as you go to this per server instance, you have to think about what is the demand from any one server, because you want to serve it locally. So that was the first step, is understanding performance, but that can be observed and studied and is known. And then the next is how do you reach that performance and make it as efficient as possible so you can actually scale it at a reasonable cost point. Like it wouldn't be practical to take one of those large central HSMs and try to nest it in a server. It would be like a server in a server, and that just wouldn't be practical. So the trade-offs here are really performance, and then how can you achieve that performance with as low power and as small an area as possible. And these are kind of competing forces, and we can get into that in a little bit. But one of the things that we had in our favor in trying to go and build this was cryptography is fairly standardized. And it's heavily standardized. In fact, the first rule of cryptography is you shouldn't design your own cryptography. So the math and scalar multiplication and encryption lends itself well to dedicated circuitry. So we could build these small crypto engines that were very lean compared to having maybe a general purpose core or programmable core. We could actually build hardened logic. But the design didn't stop there. So once you build these engines, you're faced with the challenges: how fast do you make them run? How fast can you make them run? What frequency can they go to when you can still close timing without getting, you start to get power leakage too if you push it too high. And then the flip side of that is how many instances can you put in? This is the other competing force. When you put in lots of instances, you have more keys in flight. More keys in flight means more memory, means more register state. That, again, increases area. So then you're faced with this power and area dynamic as you go through the design, and you're trying to be as efficient as possible. So we finally ended up at what we thought was a really good point, number of engines, frequencies that we're running those engines at, and we had a great cost point for the chip, and we had solved this problem. Then we had another constraint. So it's a security chip, so it has to be highly secure. So it has packaging constraints, and it has to be an anti-tamper package that goes over that chip. It's got to be resilient to physical tampering. So that brought back in some new constraints into the equation as we tried to scale it, which had us again go back and look at the power and the area. One of the challenges with this anti-tamper packaging is you can't have slits or ways for probes to get in there, so it has to be fully sealed, which then brings down those thermals that you can realistically achieve. So it brought us back in trading frequency, and then the packaging is expensive too. It makes up more than a quarter of the cost of the chip. So the packaging itself was expensive, so we didn't want to blow out the area either. So where did we end up in all of this? Well, we targeted millions of crypto operations per second, which we achieved with the chip. The crypto engines were fully hardened. So we had to forego some programmability, but security being heavily standardized wasn't necessary anyway. The only embedded cores facilitate control logic. As a PCIe interface with virtual functions for directly binding to VMs and virtualized workloads. It also supports TDISP, which is a confidential compute protocol that we worked on with the PCIe SIG. And that provides secure connections to confidential VMs, which we'll get into in a little bit. And then the module, of course, was designed fully for FIPS level 3, which is the security standard for hardware security modules. The ASIC with that anti-tamper packaging, it's not just the packaging that has to be tamper resistant. There's also side channels that have to be added onto those crypto, side channel countermeasures that have to be added onto those crypto engines. We also extend some of those tentacles for tamper detection out to the system level and have chassis intrusion and other capabilities in there. So we landed with this chip. The package is 12 by 12, so about a ½ inch. It's tiny, but it packs a mega punch in terms of its performance. That's not my hand there, although it's quite a pretty hand. That's my PM, Glenn Ward, holding up an actual chip, and they removed the background from it. So that was Azure Integrated HSM. I want to switch now and talk a little bit about confidential computing and being secure by default. Confidential computing is about workload isolation on the CPU. And it's anchored in hardware. The capabilities have to be throughout hardware. So this is it's not intended to be a marketing slide, but what I want to show, Greg, I don't know if he's still here, he gave me a hard time in a pre-review saying, hey, hot chips, we don't do marketing slides, don't put up a marketing slide. It's not intended to be a marketing slide. I just want to show you confidential compute is already pervasive. This isn't nascent. There are services already running in this. Azure runs its own workloads inside it, its own high assurance workloads inside in confidential compute environments, and many of our customers do too. So as we get into what confidential compute is, well, you remember, this ecosystem is already quite vibrant. So confidential compute is a technology designed to protect workloads such as VMs from all other software, including the hypervisor. It complements encryption at rest, which is encryption as it's written to disk, and it complements encryption in transit, which is encryption as it goes over the network. And it does this by encrypting data and code in memory and then protecting it inside in a trusted execution environment when it's executing on the CPU. And these trusted execution environments are cryptographically measured by the hardware root of trust. The hardware root of trust is an important element in confidential computing. It anchors the chain of trust in hardware and provides integrity assurances to workloads running on the hardware. So as workloads get to talk directly to the hardware root of trust to understand the security of their environment. The root of trust is a hardware anchor, and it's table stakes in secure devices. So on this root of trust, realizing how critical it was, in 2022, Microsoft, AMD, Google, and NVIDIA got together and developed an open source root of trust. It's called Calyptra. It's an open source silicon root of trust. The silicon, the RTL, the firmware, everything that runs on it, the cryptography, the side channel countermeasures, the crypto engines, all open source. Test validation criteria, everything is open sourced in it. And earlier this year, we released the second version of that chip. It's Calyptra 2.0. This builds upon the first version and adds more layers of defense and more functionality. It provides a complete security subsystem that can be taken and built into any chip. As part of Calyptra, we included Adam's Bridge, an open source quantum resilient cryptographic accelerator. I heard earlier IBM talk about how they've added quantum cryptography to their silicon too. Okay, with all new technologies, always comes new risks, and with quantum computing, it poses a risk to cryptography. The classical algorithms used pervasively today in hardware and software, can be easily defeated by a powerful enough quantum computer. So when you have Calyptra 2.0 with Adam's Bridge, it can prevent that in the hardware. And then we're extending Calyptra further. We're adding a key management block specifically for NVMe devices. And NVMe devices, they do a lot of key management for encryption of data on disk. One of the attributes that Calyptra has is it shields keys in the hardware. So even firmware running inside in Calyptra cannot get access to those keys. So a little bit about Calyptra. Calyptra by the numbers, I'll call it. It's about 1.6 million gates. 62% of the logic is dedicated to the crypto engines, including the accelerators, the side channel countermeasures, the key management, the hardware for performing key management. This reusable block provides full secure boot, measurement, attestation, key management, and recovery. You can see the various components of it and their gate count. We keep that out there. The first question I always get asked is, what's the size of Calyptra? So it's 1.6 million gates. Not large by today's means. Due to the mixed nature of open source software, open source is somewhat, its reputation is somewhat tainted for being low quality. There's some very well maintained open source software projects out there, but there's also a lot of, maybe subjectively maintained open source software projects. So the second question I always get asked about Calyptra is, how do we maintain a high quality bar? And all major silicon vendors are integrating Calyptra into their products. There's a tremendous amount of rigor that's put in to maintain that quality. Every release follows a validation plan. CDC, RDC, lint, synthesis, all have to run clean, no exceptions. A label is created, documentation is created, the validation results are published, test benches, test cases, all of that collateral is open sourced. So you go and look at it. The other question I get asked, the third question, is why open source? Why open source silicon? Open source is quite common in the software world. It's not that common when it comes to hardware. And when Calyptra was first founded, it was founded on the principles of transparency and consistency, and driving that into the hardware ecosystem. Our ecosystem was badly fragmented. So transparency is an important element in confidential computing. Since since the root of trust anchors the chain of trust in hardware, how do we have assurance on that? And the answer to that is transparency. Consistency is another challenge. When we want to have scale and we want to have secure by default, on by default, we need consistency. So consistency helps to facilitate secure by default. And then there's also standards. Cryptography, been heavily standardized. There's not a whole lot of room for differentiation. You want to do standard cryptography. As I mentioned earlier, first rule of cryptography is don't write your own cryptography. And then the last reason for this was really fortification. And fortification meaning building layers of defense. The counter argument to this is, hey, let's just be diverse and have random implementations. And that one's not even wrong. It's the only way to describe that argument is diversity. It's not even wrong. The diversity is spread betting. And betting is based on luck. And in security, you don't want to be lucky. You don't want to base your security on luck. Remember, the attackers only have to be lucky once. You'll have to be lucky all the time. And their expertise, their skill is finding the weakest link. They hunt for it. They're highly skilled at finding it. So the way to address that is really fortification, building multiple layers of defense, as opposed to spread betting and going with the diversity approach. So the fourth question I get asked is, this is great. How do I get involved? Well, there's Calyptra.io, which will bounce you to Chips Alliance, which is the open source Git repos for all of this collateral. And then there are weekly calls, and how to get involved is all up there in those Git repos. And then there's also an open compute security work group that meets weekly and talk about some of the bigger topics related to hardware security. So just to recap, SFI sits at the core of Azure's approach to designing hardware systems, from purpose-built silicon to new hardware architectures like confidential compute, to new modes of operation like the reinvention of hardware security modules. So with that, I'll thank you and take any questions. Is that right, Greg?
Thank you.
Yeah.
Do we have any online questions? Yes, please.
I don't know whether people are going for lunch or going for questions.
Oh, wait, we have, let me start with the, yeah.
Thank you. I know people might wonder who the heck asked question right before the lunch.
And who are you asking a question before lunch? Your name and affiliation, please.
Yes, my name is David Pan. Was from Linux Networking Group. Now it's part of AMD Networking Group. And this is a fantastic security slide decks and presentation. Thank you, Bryan. So my question is more like the AI workload. So let me keep my question short. So AI workload has impacted so many silicon design, and I wonder how AI workload impact the security here, or maybe to be more specific, how it impact your presentation content here, what might be the future we should focus on more.
Yeah, absolutely, yeah. And I'll say in AI workloads, confidential compute, it's one of the, it's a big driver, AI and confidential compute, where you want to have provenance, you want to have transparency, you want to have security of sensitive data. And, I know in NVIDIA, H100 supports confidential compute. So I think the AI infrastructure absolutely needs to be confidential. It's already playing in that ecosystem. It's the rest of the periphery now need to catch up with the major silicon providers and get involved in the same ecosystem. But it unlocks new modes of operating for AI, especially when it comes to multi-party sharing, where neither party has to disclose their raw data. Instead, they can share the computational results as opposed to the underlying data.
The left-hand mic, please.
Hi, thanks. Very interesting presentation. Just with all that openness that you're saying, that sounds fantastic. Very simple question. Is the HSM chip that you put in the Azure servers, is that available for people to purchase?
So, sorry, I didn't catch your name at the start of that.
Alan Cantlett, Nalisway.
Hey, Alan. Yeah, that's, that security module is available this year in Azure servers. It's not available off the shelf, to purchase from like silicon vendors or people maybe that sell HSMs. But we're definitely open to that in the future, especially with models now of external HSMs and just geodiversity and some of the work going on there with sovereignty and data sovereignty and key sovereignty. So definitely aware of it and looking into what channels we can open up to help that. We think this model makes perfect sense, and we do expect to see it expand out into other markets, not just cloud.
I guess my only point, and maybe I'm not fully understanding, but with all this openness, if there's a new startup wants to necessarily adopt this, then I guess they have multiple choices for where to get the HSM, is what you're saying.
Yeah, and if it's the silicon logic that forms the HSM, like in this open source code, absolutely. Like the accelerators and stuff that we create, you will see some of those in Calyptra with that Atoms Bridge, quantum accelerator, and so on. So yeah, open source, and will enable channel partners for the Azure HSM, and the firmware will be open source.
I think we'll take one
Larry.
last question online. Okay.
Yeah.
Sorry. There'll be lunch, sorry.
I'll catch them later.
Yeah, just wait right here. We're going to get people to lunch in a minute.
Yeah, this question is on distributed roots of trust. So it seems that Azure server system is a distributed system of roots of trust where each CPU, GPU, SmartNIC have their own roots of trust. So how do all these roots of trust come to a consensus that the data center rack is a secure state?
Yeah, that's a great question. I didn't catch who asked that, the name again.
Well, you know what? Maybe for this, I'll ask you to answer it on the Slack channel.
Okay, I'll answer that
okay?
question on the Slack channel.
Okay,